Hello and welcome to chapter 13, the integral. We're not going to do every section in this chapter. We're just going to do three of them, 13.1, 13.2, and 13.4. Let's start with 13.1, the indefinite integral. We're going to start with a definition. An antiderivative of a function f is a function capital F such that f prime, capital F prime, is equal to little f. All right, so antiderivative, opposite of the derivative. So now we're going backwards. For example, an antiderivative of 4x cubed is x to the fourth. Why? Because x to the fourth has derivative equal to 4x cubed. So antiderivative is where the derivative came from. Another antiderivative of 4x cubed is x to the fourth plus 2, or x to the fourth minus 17. An antiderivative of 2x is x squared plus 11. See, the thing is we can't ever recover a constant, right? Because what's the derivative of a constant? It's zero. Going back from zero in an antiderivative, we have no idea what constant it could be. So if the derivative, right, if the derivative of a is b of x, then the antiderivative of b of x is a of x. All right, so it goes the other direction. Now here's our symbology. This is it's an elongated S. It really is an S, and it's for sum, and we'll see that in a little bit. The integral of f of x dx is read the indefinite integral of f of x with respect to x, and stands for the set of antiderivatives of f. All right, so this is a collection of functions, just like this tells us to take the derivative of f of x, where x is your variable. This says take the antiderivative of f of x, where x is your variable. It's not a single function, it's not a number, it's a whole collection of functions that are different just by the constant. The function f is called the integrand, it's inside the integral, it's being integrated. The variable x is called the variable of integration. Okay, so think about it. You have the derivative, and you want to find the original function. Since the derivative of a constant is zero, we have no way of knowing what the original constant was, as I mentioned up here. So we use a general C, a capital C. Make sure it's a capital C if you're using online homework systems. Sometimes it really matters that particularly. So we use a general capital C in its place that gives us the family of functions. This is known as the constant of integration. It allows us to go from talking about an antiderivative to the antiderivatives. All right. So just like there were rules for finding derivatives, there are rules for finding antiderivatives. I don't believe we're going to do the detailed, like we did the limits before derivatives. I don't think I'm going to make you do too many sums before we do antiderivatives. These rules, absolutely, since they're the opposite of derivatives, are going to be very similar to ones we had earlier. Okay, so part one. The integral of x to the n dx is x to the n plus 1 over n plus 1 plus c if your n value is not equal to negative 1. What happens if n is negative 1? Negative 1 plus 1 makes a division by 0. That's an issue. So the special case is when n equals negative 1, but we know that x to the negative 1, that's 1 over x. We happen to know a function that has 1 over x as a derivative, so the antiderivative is right there, the natural log of the absolute value of x. Now, in general, we took the derivative of the natural log of x to be 1 over x. It's absolutely important that the absolute values go on the natural log and the antiderivative. Because when we're recovering this x here, it's given to us, we know our domain is being taken care of. When we're doing the antiderivative, we have to put the absolute value on to make sure that our domain remains appropriate for the natural log function. So without absolute values, that's incorrect, many times. Our exponential rule, we know that the derivative of e to the x is itself because it's awesome. So the antiderivative of e to the x is also itself plus a constant. If b is any positive number other than 1, so it's the base of an exponential, the integral of b to the x dx is b to the x divided by the natural log of b plus c. For example, the integral of 2 to the x dx is 2 to the x divided by the natural log of 2. Just like when we had the derivative of, say, 3 to the x, our derivative was the natural log of 3 times 3 to the x. When you take the derivative of an exponential with a different base, you have to multiply by the natural log of the base. Well, taking the antiderivative, we'll divide by the natural log of the base, undoing this operation. Now, sums, differences, constant multiples, just like for limits, just like for derivatives, just like for all of our good mathematical operations, the integral of a sum or difference of functions is the sum or difference, respectively, of the two integrals. Constant can be brought in front of the integral, so we can find the integral of f of x and then multiply by our constant, just like when we did derivatives. K times f of x, we know that was k times the derivative of f of x. All right, same idea with antiderivatives. Let's do a bunch of examples. Let's look at these 4. The integral of x to the 7th dx. I'll find the integral. I'll use integral or antiderivative interchangeably. All right, they're the same thing. Just one is shorter to type. The antiderivative of x to the 7th dx is x to the 7 plus 1 divided by that new power, 7 plus 1. Don't forget plus c. So that's x to the 8th over 8 plus c. Number 2, the integral of negative 5 dx. Well, what has derivative equal to negative 5? Negative 5x does. So the antiderivative of negative 5 is negative 5x plus c. Always plus c until I tell you different, which will probably be in the next section. So the integral of x plus x cubed dx, we can use our sum and difference rule and take that apart. That's the integral of x dx plus the integral of x to the 3rd dx. This is x to the 1st, so I'll have x to the 1 plus 1 over 1 plus 1, plus the integral of x to the 3rd dx is x to the 3 plus 1 over 3 plus 1. Notice that this integral sign and the dx, they go together, right? They work as a team. They're telling you exactly what to do. So in this process, the integral of x dx, the integral and the dx are used up in getting the x squared over 2. Right? So they're a pair. They come together just like this d dx was a pair, and it told you what to do. The integral of 4 minus x dx, that's the integral of 4 dx minus the integral of x dx. The integral of 4, what is the antiderivative of 4? The opposite of the derivative? Well, that's 4x. Minus x to the 1st. We already did it over here, so let's not reinvent the wheel. That's x squared over 2. So our final answer will be 4x minus x squared over 2 plus c. Take the derivative. Derivative of 4x is 4. The derivative of x squared over 2 is 2x over 2. Notice that when we, and derivative constant is 0. So when we find the derivative of our answer, we should get this right here back, right? The integrand. All right, more examples. The integral of 1 over v squared plus 2 over v dv. So v is our variable. I split them. That's the integral of 1 over v squared dv plus the integral of 2 over v dv. I rewrote 1 over v squared is v to the negative 2. So the integral of v to the negative 2 dv. I took my constant 2 out in front. 2 over v is 2 times 1 over v. So I pulled my constant out in front. 1 over v is very special, right? That's a v to the negative 1 power. So when I do the antiderivative, I'll use the power rule. The integral of v to the negative 2 dv, I'll take negative 2 plus 1 to be my new exponent, and that's my new denominator as well. Plus 2 stays out in front. The antiderivative of 1 over v, special rule, that's the natural log of the absolute value of v, plus c. Negative 2 plus 1 is a negative 1, plus v to the negative 1 over negative 1 plus 2, absolute value of v plus c. And then I just tightened it back up. Instead of v to the negative 1 over negative 1, I made that a negative 1 over v. Take the derivative. Make sure you're right. You can always check your answers. This isn't history. We don't need a phone booth. We can check our answer straight away. Integral of 4x to the 7th minus x to the 3rd dx. I'm going to pull the 4 out in front of the integral of x to the 7th dx minus the integral of x to the negative 3 dx. So my 4 stays out in front. My x to the 7th, the integral, I'll add 1, so it's x to the 7 plus 1 over 7 plus 1, minus the integral of x to the negative 3 is x to the negative 3 plus 1 over the same denominator, negative 3 plus 1. Don't forget your constant. Notice I write the constant as soon as I do the integral. I start writing plus c. I don't want to forget that. I don't want to get a problem wrong because I didn't put a letter when I did all of the mathy stuff right? I forgot a constant. Really, I did the hard work, and then I'm going to lose points because I forgot a constant. So I remind myself right away. 7 plus 1 is 8. Negative 3 plus 1 is negative 2. So I simplify 4 over 8, right? That's the same as 1/2 x to the 8th. A minus sign and a negative 2. So I'm subtracting a negative. So I take the x to the negative 2 to the denominator to tighten it all up. Although it doesn't look like it was totally necessary. Always a simplified answer is so much easier to type into your online homework system if we're using one. So anybody else using this, make sure WebAssign says capital C. I'm just saying. The integral of 1 over x to the 1.1 minus 1 over x dx. I will separate them. I remind myself that x to the negative 1 is a special case. X to the negative 1.1, nothing special about it. So for the first integral, the first antiderivative, the integral of x to the negative 1.1 dx, I'll take negative 1.1 and add 1, make that my exponent on x, and make it my denominator. Minus sign. The special case, the integral of 1 over x, the integral of x to the negative 1 dx, is the natural log of the absolute value of x. Finished my integrations, so I add c. Negative 1.1 plus 1 is a negative 0.1. Dividing by a tenth, 1/10 is the same as multiplying by 10. I took my x variable to the denominator to give it a positive exponent, kept my negative sign out in front, minus the natural log absolute value of x plus c. Woo! It really is straightforward if you let yourself follow the pattern. Get in the habit of writing these plus ones for now, and in a section or two, you're not going to need them. All right, let's look at an application. The marginal cost of producing the X box of thumb drives is 10 plus X squared over 100,000, and the fixed cost is $100,000. Find the cost function C of X. Remember, marginal cost is the derivative, right? So it's saying, hey, your derivative is 10 plus X squared over 100,000. Cool. So we know the total cost is the antiderivative of 10 plus x squared over 10,000 dx. That's the integral of 10 dx plus 1 over 100,000 times the integral of x squared dx, right? It looks kind of hard here, but when we break it apart into its little bitty pieces, it's not that bad. The antiderivative of 10 dx is 10x because 10x has derivative equal to 10. 1 over 100,000 stays out front. The integral of x squared will be 2 plus 1 makes 3, so a new exponent of 3 on the x, denominator of 3, plus our constant. Now, in order, oh no, we already got the fixed constant. It already tells us the fixed cost is 100,000. So this constant, this fixed cost is the constant. Tells us that this 100,000 is specifically for this situation. A different company might find the same marginal revenue, but a different fixed cost. Maybe they have cheaper rent, cheaper electricity in their location. All right, but that 100,000 as the fixed cost, we know that's going to be our constant term. So this would be the answer, the final answer for the cost function. Excellent, excellent. Couple more. I'm going to put them both on the screen. We'll just work top to bottom. It's fine. The marginal cost of producing the xth box of CDs is 10 plus x plus 1 over x squared. The total cost to produce 100 boxes is $10,000. Find the cost function C of x. Okay, now we know C of x is always the antiderivative of the marginal cost. Whatever that marginal cost is, the antiderivative is our cost function. So we can take this first sentence. C of x equals the antiderivative of 10 plus x to the negative 2, right? Getting it calculus ready, dx. Instead of writing this again with integrals, we could just do this, right? The antiderivative of 10 is 10x. This is x to the first power, so the antiderivative of x is x to the 2 over 2, so x squared over 2. And the antiderivative of x to the negative 2 is x to the negative 2 plus 1 over that same value for the denominator, plus c. Simplify everything. 10x is good, x squared over 2, x to the negative 1 over negative 1 plus c. Cool. Second sentence. The total cost to produce 100 boxes is $10,000. So when our input is 100, our output, our cost is 10,000. So we're going to take this function written in an algebra way, right? So instead of plus x to the negative 1 over negative 1, I'll call that minus 1 over x. Everything else is the same. So my cost is 10,000. The rest of the equation stays put, but my x value is now 100. I can find the value on the right. It's $5,999.99 plus c. Subtract $59.99.99 from both sides. 10,000 minus nearly 6,000 is $4,001 equals our constant, the constant that we were looking for. That gives us a final answer of our total cost function for this situation. If you're given a fixed cost, it is your constant. If you're given a point, a specific value, that's how you find your constant. But in these application problems, you will probably never have a plus c at the end. You'll need to find that constant value. All right, last example. The velocity of a particle moving in a straight line is given by v equals 3e to the t plus t. Remember, particle motion, we use time as our input. Find an expression for the position after time t. Remember, we have position, and then we have velocity, and then we have acceleration. So velocity is the derivative of position. Position is the antiderivative of velocity. I'm given a velocity. I can find my position by finding the antiderivative. I can pull my 3 out in front. That's just a coefficient. 3 times the integral of e to the t dt is 3e to the t. The integral of t dt is t squared over 2. Don't forget your plus c. All right, so that's a great first equation. It's an expression for the position after time t. But now, given that s equals 3 when time is 0, find the constant of integration c, and hence, find an expression for s in terms of t without any unknown constants. Okay, so when t is 0, s is 3. So I put 3 on the left equals 3e to the 0 plus 0 squared over 2. E to the 0 is 1. 0 squared is 0. Divided by 2 is still 0. So I'll have 3 plus c equals 3, and c must be 0. And so my position expression is 3e to the t plus t squared over 2 plus 0 if you feel like writing it, but not entirely necessary at all. All right, the integral. All right, some basic rules. Put them on a note card. Write down as many steps as you need to along the way. Perhaps eventually you'll get to, hopefully eventually in a week or two, you'll get to this point where you don't have to write down every step anymore. But take as much time as you need. Thanks for listening.